Okay, so this is our third polar form of complex number videos, and this is where I take the Maclaurin series ideas and connect them with the r and cosine theta plus I sine theta idea. And so, in order to do this, what I'm going to do is write down our Maclaurin series and then do a substitution into each of those Maclaurin series and show you how they are connected. And this is really nice idea because it brings together some different types of math that may not on their face seem like they're connected to each other. So first, please remember that the Maclaurin series for e to the x is 1 plus x squared over 2 plus x cubed over 3 factorial plus x to the fourth over 4 factorial dot dot dot. As long as I want to go, the important thing is that it's x to the nth power over n factorial, and I could go infinitely long. And remember, Maclaurin series is just the function, its derivative, its second derivative, its third derivative. And as you go along, you're just dividing by the n factorial. Okay, so let's do sine of x then. So sine of x, the sine of 0 is 0, so we skip that term. The sine, then the next is cosine of 0 is 1, and then we skip the next one, and we have a negative 1, so we have negative x cubed over 3 factorial, and then we have positive x to the fifth over 5 factorial, and then negative x to the seventh over 7 factorial, plus dot dot dot, plus here what we're seeing is that there is an odd power, and the value on the bottom is also odd, and it's a factorial, and we have a alternating sign, so it alternates back and forth from positive and negative. You really don't need to worry about that general term that I wrote on the end. What I want you to think about is just notice how they're kind of similar. E to the x has all the powers and they're all positive. Sine of x has all the odd powers and it switches from positive to negative. Okay. So now let's look at cosine of x. Cosine of x goes 1, and then you do the derivative and you get sine, and that's 0, and you do the derivative and you get negative cosine, and so you have minus x squared over 2 factorial, and then it flips back to positive x to the fourth over 4 factorial, and then it flips back to x to the sixth over 6 factorial, dot, 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 and all of that comes to be negative 1 to the n, x to the 2n, and 2n factorial. And so what I hope you're seeing here is that these are similar things. Sine has all the odd powers, cosine has all the even powers. So the insight that we had, and I think it may have been Euler, the mathematician Euler, who had this insight. Don't quote me on that, but that sounds right off the top of my head. The insight was, well, what if we did, instead of e to the x, what if we plugged in ix? And so what I'm going to do is go back to my original e to the x formula, and instead of plugging in x, I'm going to plug in ix. So it's not 1 plus x, it's 1 plus ix. Then it's ix squared over 2. And then it's ix cubed over 3 factorial. And it's ix to the fourth over 4 factorial, blah, blah, blah. Now, if you think back, okay, what does I to the different powers mean? Well, I squared is negative 1, I cubed is negative I to the fourth is positive 1 again. So I can rewrite the values that I just got as 1 plus ix minus x squared over 2 minus ix cubed over 3 factorial plus, then it would be x to the fourth over 4 factorial. Oops, looks like we jumped around there. X to the fourth over 4 factorial. And what I hope you notice is that we actually have here the sine and the cosine Maclaurin series combined together. Let's use some different colors to try to illustrate this here. In the blue, I'm going to draw cosines. Here's a cosine term. Here's a cosine term. This next one that got cut off would be a cosine term. See how they match up right here? The ones match up. The negative x squared over 2 matches up. The positive x to the fourth over 4 factorial matches up. Let's use green to show sine. X is in sine. X is right there in there. X to the third over 3 with a negative on it. X to the third over 3 with a negative on it. And this is going to continue to pattern. And so the pattern will continue. And what you can see is that it's always going blue, green, blue, green, blue, green. That the cosine values are all real, because when you raise I to an even power, you get a real number. And so every other term is a real number, and every other term in between is an imaginary number. And the real parts are all the expansion of cosine, and the imaginary parts are all the expansion of sine. So putting all of that together leads to this pretty remarkable conclusion that e to the ix is really equal to cosine of x plus I times sine of x. And really, just to go back to the colors, all I'm saying is that the e is represented by the blue parts plus I times the green parts. Okay? So putting that all together leads us to this great conclusion then. I'm going to clear the screen here. We talked about in the other videos how you can take any complex number as a plus bi. You can think of that as a point on the plane, a comma b, and you can represent that in terms of r and theta. And then we talked about how, well, okay, if you can represent it in terms of r and theta, you can change that and write it as r times cosine theta plus I sine theta. What we talked about in this video is how, I'll use a different color for this, e raised to the ix can really be cosine x plus I sine x. So the grand finale is putting all of that together and saying, okay, any complex number, a plus bi, can be represented as r times e to the I theta. It's really a pretty astonishing result if you think about it. And just because I would be remiss if I didn't mention, there's a meme that goes around. You see it on Math Nerd sweatshirts, or some people even have it tattooed of this wonderful equation where they write e to the I pi plus 1 equals 0. And now we should understand why that is a true statement. Thanks for watching. Please ask for more videos if you need them.